there, if you have read financial newspapers in the last months, you have probably read about stress testing. What is stress testing? You have probably read about the fact that now, under Basel III, banks are required to perform stress testing in order to take into account the risk of extreme events. And this is true for market risk and for credit risk. So, the aim of this class is to introduce you to stress testing.
A stress test is a procedure, a way to determine the ability of a given financial institution, typically a bank, to cope with an economic crisis or bad economic conditions in general. Using stress testing, a bank must answer questions like what happens if interest rates increase by at least X%, what happens if the correlation among defaults increases, and so on. Thanks to Basel III, stress testing has become increasingly important. It is now a regulatory requirement for large international banks, which must prove to have adequate capital allocations to cover potential losses due to extreme but plausible events. A stress testing procedure is usually based on the so-called scenarios. A scenario is simply a given configuration of parameters and variables for the model we use in assessing risk, credit risk in our case. The idea is simply to see what happens for unusual values, a scenario of macroeconomic quantities such as interest rates, inflation rates, unemployment rates, volatility, and so on. We want to see what happens to our risk measures and capital requirements under particularly stressed conditions. From an operative point of view, stress testing is performed using computational and statistical tools such as Monte Carlo simulations, extreme value theory, and, as the statisticians among you may guess, sensitivity analysis. We can use a simple example to give an idea of how stress testing works. Assume that for estimating the probability of default of a counterparty and, as a consequence, the capital requirements under the Foundation internal rating-based approach, we use Merton's model, so that the one-year probability of default of our counterparty is given on your screen. Check week 5 for more details. Now assume that R, the interest rate, is equal to 0.02, V0 is equal to 22, B, the liabilities, are equal to 16, and sigma V is equal to 0.2. Then the one-year probability of default is 5.57%. A simple scenario is to assume that sigma V increases to 0.5 or 0.8 or even 1 and see what happens to the probability of default. Using the three values of sigma V, we see that the probability of default of our counterparty dramatically increases. All this is likely to make our capital requirements increase as well. Do we have enough capital for that? A bank decides if it is ready to cope with such extreme cases by computing the capital requirements under different scenarios. The regulator usually decides which scenarios need to be taken into consideration when computing capital allocations. The previous example is just a trivial one. Naturally, we can also think of more complex scenarios in which more than one single element changes. This is what banks do using complex computer programs. Scenarios may be produced on the basis of historical evidence, expert judgments, decisions of the regulator. Historical evidence means that we want to test how we are able to cope with extreme scenarios we have already observed in the past. When dealing with expert judgments, we want to test hypotheses developed by economists about future trends and cycles. Finally, there are cases in which a specific scenario may be imposed by the regulator. This is something that changes from country to country. For example, it has become rather common in Europe, where the European Central Bank really insists on stress testing. Apart from scenario analysis, another way of performing stress testing is to use the so-called stressed measures of risk. These are the same measures of risk we have seen together, but we use them in more extreme situations. A simple example is the stressed value at risk. Developed for market risk, stressed VaR, also known as SVaR, is now popular in credit risk as well. The computation of SVaR follows the rules of value at risk, but we only consider the worst losses, the worst scenarios, typically the worst 50%, that is, the largest ones. A simple example in R is the best way to understand stressed value at risk. Assume we know that our losses are log-normally distributed with mean 1 and standard deviation 2. Let's start by generating 100 losses using the function RL_norm. This is just an example. In real life, one typically uses historical data. As usual, we can plot a histogram to see how our losses are distributed. The 95% VaR is easily obtained using the quantile function, as we have already seen. The command is quantile losses 0.95 type equal to 3. Type equal to 3 means that we want to identify the closest value in the data without interpolation. I suggest you to type $quantile to check again the properties of the quantile function. Our value at risk is 61.48. In order to compute the 95% stressed VaR, we first sort all losses from the smallest to the largest. Then we select the top 50%. In our case, with 100 losses, this means the 50 largest losses. We store these losses into a new variable. Then we can again apply the quantile function. The stressed value at risk is 155.17, much larger. This value at risk is in fact computed on the worst losses. Have you noticed that the 95% stressed VaR corresponds to a 97.5% value at risk on the original losses? Could you say why? My suggestion is to think about 1 minus alpha.
Okay, see you next time. Bye!